In this video, we'll be going over positional probability and entropy. So we'll be actually using the idea of positional probability to explain a concept called entropy. So for years, scientists they were looking for ways to explain why certain processes are not are only observed spontaneously happening in one direction. For example, iron rusting on a car, like the iron oxide doesn't come back and make iron and oxygen, the iron oxide compound. So same thing if you burn, some type of fuel, like you have a campfire, those gases that come out of the wood burning are not going to come back and make a log again. So for a long time, scientists thought that processes that were exothermic were that was like the driving factor, the fact that the process was exothermic. But they came to find out that it's more something to do with kind of like the most probable arrangement of things happening. So let's describe how this works. So a certain process has more possible arrangements. If a certain process has more possible arrangements, that process favors the state with the most probability of happening. So these states are called microstates. So the key ways to increase the number of microstates are to increase the volume, increase the temperature, or increase the number of molecules. So to illustrate this example of what a microstate is, we'll use this like this flask, or kind of like this tube with bulbs on it. Okay, and then let's say that we have two gas molecules, A and gas molecule B. So we have molecule A and we have molecule B. Okay, and these molecules can be, and let's say um, the state that's favored is going to be the one that's most mixed, where these two molecules are. So let's say these two molecules are in this container. So we have molecule A and molecule. Actually, let's just say they're right here over here, and they're going to be added to this container. So there's a couple different arrangements that they can do. So the most probable arrangement is the one that's going to have the most possibilities. So we see that there's a statistical dependence on entropy, this idea of randomness or disorder. So let's say we have our I tried to draw those equally sized there, but okay, so we could have one where A and B are both on the same side. There's only one possible arrangement of that. Okay. Um, where they're both on the left side. Okay, and where they're both on the right side, there's only one out of four where it's so this is one out of four where they can both be on the left. Both on left. Okay, and then this is one out of four where they're both on the right. Okay, but there are actually two arrangements where the A and B are distributed throughout the container. So there's one on each side here, and then there could be here, B could be here, and then A could be here. So there's actually two out of four arrangements where the molecules are actually mixed. Okay, where they could be on one on each side. So this doesn't seem like that crazy of an idea until you get to like Avogadro's number of molecules. So if you have 1 mole, what if instead you had, instead of just two gas molecules, what if you had a mole of gas molecules, 6.02 times 10 to the 23rd molecules? Okay, what are the possibility that one whole mole is actually on one side of this container? So that that probability is so small that it's essentially never observed, that all if you had a whole mole of gas molecules, that they would be arranged all on one side of the gas molecule all on one side of this container. So in the next slide, I have a couple different pictures here. This is where we have four gas molecules. So instead of just two, I had four. So that you could see that as you increase the number of molecules, the number of microstates increases. So here you could have four on one side and four on one side. So two out of six where they could be on one side of the container. But the ones that we could say are mixing, where there's 3 and 1 or 2 and 2, there's 3 and 1 in four possible states. Okay, and then where there's 2 and 2, there's actually six out of the whole possible number of arrangements. So the whole possible number of arrangements is 10, 11, plus five more. So we have 16 possible arrangements. So six of those 16 arrangements have them mixed, where there's two on each side. So you could see that if we had a whole mole of gas molecules, this middle number where they're fully mixed is going to be massive. Okay, and that's going to be the most favored state. And in fact, that's what we see. So, and there will be one out of 6.02 times 10 to the 23rd. There's only one possibility out of 6.02 times 10 to the 23rd that will look like this. Okay, and then the most massive probability would be this middle one where there's equal amounts on both sides and it's equally uniformly distributed. Okay, so that's the concept of microstates. So what does that have to do with entropy and the second law of thermodynamics? So how do microstates apply to whether a process happens spontaneously or not? Back to our log burning, okay, and then the gas molecules not coming back. Okay, so consider the following. Okay, these are all, things that have been observed. So a ball rolls down a hill but never spontaneously goes back up a hill. Okay, so if exposed to air and moisture, steel rusts spontaneously. However, the iron oxide in rust doesn't spontaneously change back. This is the example I brought up earlier. Okay, heat flow always occurs from a hot object to a cooler one, and the reverse process has never been observed. It's never occurred spontaneously. Not never been observed, but never occurs on its own spontaneously. Okay, so at temperatures below zero, water spontaneously freezes, and at temperatures above zero, ice spontaneously melts. So this one is kind of interesting because we see that there's actually a temperature dependence also on entropy. This is something we'll be dealing with in the next video. So there's a temperature dependence for entropy as well. Okay, so in this case of steel rusting, you're going to see, if you look at the atomic arrangement, you're going to see much more disorder among the iron and oxygen atoms. Okay, if you look at the atomic arrangement, so things tend to spontaneously move towards a state of more disorder. Okay, because it takes, if we go back to our microstate picture here, it takes a lot of order to get these in there. Okay, it can be done, and it can be done if you push it over. So if you add some form of work, or you actually have to put energy in, usually, to do these kinds of microstates. But the ones that happen on their own, if you leave this situation onto its own, this is the most probable arrangement. Okay, same thing with the gas molecules not coming back. So it's really hard for them to come back and make the log again. They're going to go off and make gases. Okay, and so they're just not going to come back. So if we go back to here, we can make the following conclusions about entropy. So I need to erase what it wrote there. So all of these have a most probable microstate for their molecular arrangement, all of these processes here. So it's the state which favors the most randomized or disordered arrangement. So simply because there are many, many more of these than the ordered ones. So going back to the previous slide with the two bulbs and the gases being equally distributed. So many more that the ordered state is simply not observed. Okay, so a state which favors more order, a state that favors more molecular disorder in the universe is the direction a process will go. Okay, and then this molecular disorder is what we call entropy. Okay, so here's the your turn. Okay, and we're going to try to ask the question, how these following changes affect the positional entropy of a substance. So go back to the first slide, and I went over the effect of increasing pressure, increasing volume, and increasing temperature on the number of microstates available. So see if you can reason 1 and 2, like which ones you think will show an increase in entropy or disorder, okay, or an increase in number of microstates. Okay, so that's the end of our introduction entropy video.